So this is joint work with Shafi Goldwasser and Ofer Grossman, and today I will be talking about pseudo-deterministic proofs. Can everyone hear me all right? Okay. So first, we'll define pseudo-determinism. So a pseudo-deterministic algorithm for a search problem is a randomized algorithm that on the same input will output the same output with high probability. And so this is different than simply guaranteeing that the answer is unique, in that this is a more relaxed version of that. So what are some nice properties that pseudo-deterministic algorithms have? So one of them is reproducibility, in that if you run the same algorithm on the same input, even with different randomness, it will output the same answer with high probability. And in addition, we have this correctness amplification where you can now take the majority of the inputs and get a single answer. Whereas usually when you have a randomized algorithm for a search problem, there are too many answers for this to be practical. So what is a search problem? So a search problem is you're given an input, x, and a relation, and you want to determine a y such that xy satisfies the relation. So specifically, we can consider the class search BPP, which is the class of problems in such that finding such a y is in BPP, and that you can test that xy is in R in polynomial time. So what do we know how to do already? Already we have pseudo-deterministic algorithms in the sublinear setting. We have pseudo-deterministic algorithms for parallel problems, such as bipartite graph matching, and we have a sub-exponential time pseudo-deterministic algorithm for finding a prime for infinitely many input lengths, given the length of the prime that you want. And in subsequent work, I was able to show an average case sub-exponential time infinitely often pseudo-deterministic algorithm for every problem in search BPP. So what are we going to do today? Today we are looking at specifically this notion of pseudo-deterministic interactive proofs, which we are introducing. And so what is this going to entail? We're going to have a prover and a verifier. And in addition to the sort of standard completeness where the honest prover gives you the right answer, and soundness where no cheating prover will be able to get you to output a wrong answer, there's also this notion of canonical soundness, which means that no cheating prover will be able to make you output a different answer than this so-called canonical answer, which varies from problem to problem. So here we see the prover and the verifier. And so we wanted to output a y or reject, is what the verifier is going to do. And so we have our completeness and our soundness, which is standard. And then again, this canonical soundness means there's some y such that the prover cannot get you to output a different y with high probability. So one application of this is if we want to generate parameters for, say, Diffie-Hellman, where you need like a prime and a generator, but you don't trust the central authority to do this. So what you can do is you can run a pseudo-deterministic interactive protocol with the central authority to prove that these objects were generated in a canonical way and not according to some adversarial algorithm. So here are some related notions that we want to clarify the difference between. So Valiant-Vazirani had this randomized reduction from SAT to unique SAT. But in our case, we don't need that there is a unique answer for every input. We just need that the verifier will output the same answer with high probability for each input. And in addition, there's this notion of single-valued NP functions, which is where you have an NP function where every branch outputs the same output. And this can be thought of as a deterministic version of what we're going for here, because instead of outputting the same answer with high probability, it'll output the same answer with probability 1. So let's start by talking about unbounded round proofs for pseudodeterminism. Now, since IP equals p-space, what we can do is we can find the lexicographically first output that satisfies the relation in p-space, and then use an interactive protocol to convince the verifier that this is, in fact, the lexicographically first output. And this works because IP is equal to p-space. So now let's move on to the bounded round case. So specifically, pseudodeterministic AM. Now, up here, we've listed the definition for 2 rounds. And as it turns out, 2 rounds is equivalent to constant rounds in this setting, much like in the traditional AM setting. And also, the power is the same with public and private coins, similarly to the traditional AM setting. And again, I want to emphasize that the honest prover lets you compute f of x with high probability, and every other prover will make you not deviate from f of x with high probability. So similarly, we can define PSDMA, which is the usual 1-round randomness interaction. So our results. The first result we have is a constant round pseudodeterministic algorithm for finding an isomorphism between 2 graphs. As in, the prover and the verifier will interact, and then the verifier will output the same isomorphism with high probability. And more generally, we can show that search P within AM intersect co-AM oracle for decision problems is in pseudodeterministic AM, and almost vice versa, in that pseudodeterministic AM is in search P with oracles for a promise problem in AM intersect co-AM. And this is also true for MA. And as a corollary for this, you can show that no NP-complete problem is in pseudodeterministic AM unless the polynomial hierarchy collapses. And in addition to this, we give a pseudodeterministic MA algorithm with a sub-exponential time verifier, sub-exponential time proof length for all of search BPP. So the algorithm for graph isomorphism. We're given 2 graphs, G0, G1, and what the prover claims to be the lexicographically first isomorphism between the 2 graphs, and then the verifier and the prover will interact to show this is true. Now, you can consider this as what the prover and the verifier are going to do is prove that this is a lexicographically first isomorphism vertex by vertex. However, this would not give us a bounded round proof, so we can do everything in parallel, and then it will be bounded rounds. And so in this illustration, the verifier will use private coins, but public coins also works. So we have these 2 graphs, G0 and G1, and we're performing this in parallel. So suppose that for vertices V1 through Vk, we've already established that these are sent to the right place in the lexicographically first isomorphism. So now we want to prove that the next vertex is also sent to this vertex in the lexicographically first isomorphism. So what does that mean? It means that there are no isomorphisms where these first vertices are sent to the places they're sent to, and that if this vertex vk is sent to any vertex before this one, there are no isomorphisms. So that is exactly what this protocol does in parallel. It says for every vertex that's before it, you want to show graph non-isomorphism between these two graphs, where first you label the first k vertices in G0, and then you label where this supposed possible isomorphism would send them, and show that no such isomorphism actually exists. So if you do all of this in parallel, this will prove that the isomorphism the prover gave you is in fact the lexicographically first isomorphism. And so let's move on to what we can consider sort of the main theorem here, which is this almost equivalence between pseudo-deterministic AM and search P with an AM intersects co-AM oracle. So the first part, the oracle contained in pseudo-deterministic AM. So first, what the prover is going to do is it's going to send the questions and the answers for what the oracle machine would have queried. Now, since the oracle machine is deterministic, these questions and answers only depend on previous questions and answers. And so the prover can just send them all to the verifier. And then the prover and the verifier interacts to verify that these answers are correct for these questions. And since this is an AM intersect co-AM problem, this can be done in AM. So if A1, say, is 1, then you run the AM protocol. And if A1 is 0, then you run the co-AM protocol. And then the verifier just runs the algorithm and checks if the queries are the right queries, and then uses the answers to those queries when it wants to simulate the oracle machine. Now, this is pretty obvious to see why this works with an honest prover. To see why a cheating prover will not be able to deviate with high probability, either the cheating prover has to lie about the answers to one of the questions, or it has to lie about one of the questions. If it lies about one of the answers, the interactive proof will catch it with high probability. And if it lies about one of the questions, then if we look at the oracle, running the oracle machine, the questions won't match, and then the verifier can just reject. So what do we do in the other direction? And why do we need this promise problem guarantee? And why can't we just use a regular sort of language thing? So what the search P machine is going to ask the oracle is the ith bit of the oracle machine the answer that the canonical prover gives you? Is that a 1 or a 0? And it's pretty clear that this is an AM intersects co-AM, because you can just run the pseudo-deterministic AM oracle and then output 1 if it's a 1. But the reason this is a promise problem is that this canonical solution doesn't always exist. And so it only exists when you have such a solution. And when there's no solution, the problem is undefined. So now let's go on to this sub-exponential time pseudo-deterministic AMA algorithm for search BPP. So what's the idea here? The idea here is we have a hard function f in sub-exponential time MA intersects co-MA. Specifically, a function does not have polynomial size circuits. So what do we do? So the prover sends over the truth table to this hard function, and it sends over all the witnesses you need to check that the truth table is correct. And so what the verifier does is first it checks that this truth table is accurate. And now that it knows this truth table is accurate, it has in its hands a truth table for a hard function. So what does that mean? It means you can use the Nissan-Wigderson protocol to construct a pseudo-random generator. So what does the pseudo-random generator do for us? It means we can now we can run the search BPP machine with the randomness given by the output of the pseudo-random generator on all seeds. And then we just pick the first one that outputs an answer that we can check that is correct using the fact that these search BPP properties are testable. And this is our algorithm. And again, the honest prover works, and the cheating prover can only lie somewhere in here. And if the witness doesn't match with the truth table, then the verifier is guaranteed to find this with high probability. And so, open problems. Here are a few open problems I've chosen to highlight. The first one is there a pseudo-deterministic AM algorithm for every problem in TFNP? Now, the reason that this might be plausible is that TFNP is widely considered to be the analog of NP intersects co-NP for function problems, which suggests that pseudo-deterministic algorithms should be possible. Also, since we know that approximate shortest vector in lattices is in AM intersect co-AM, a natural question arises whether there are pseudo-deterministic algorithms for finding an approximate shortest vector, i.e. this will output the same shortest vector with high probability with the prover. And also, as a step towards trying to find some sort of algorithm for generating a prime, we ask, is there a pseudo-deterministic algorithm given a prover for finding a prime given the length of such a prime that you want? And as I've said here, the issue is that how can the prover show that P is prime and that it has a specific property that makes it canonical, that distinguishes it from other primes of that length? Okay.